कहीं टाइम देखने का नहीं है, टाइम देखने का नहीं है कहीं। कोई बात नहीं, कोई बात नहीं। नहीं, वो बीच में देखने के लिए कितना है।
Okay, guys, let's start on time. So I would like to again, not going in detail intro, of course, but would like to welcome Dr. Arjun for this session, which is more relevant to my research domain, in fact, but overall it's a very interesting research problem of and very challenging problem also of that he's going to talk about. He has been working on this problem for quite long time now. I think before deep learning era itself, you started exploring.
2008.
Yeah, 2008. So it's almost 15 years that he has, 14 years that he has been exploring that. So just ask questions, whatever you have any interesting things that you want to get clarity on. So now over to you, Arjun, to take us through
this. Thank you, Avinash. So welcome all. If people sitting at the back would like to, move ahead, feel free to do that. So the topic for this session is 3D humans. You guys can hear me? From 3D humans to stick figures, from 3D humans, from stick figures to digital avatars. So I'll show you what I mean by stick figures, and I guess digital avatars is kind of a self-contained word. So what I'm gonna talk about today is some of my own work. I mean, so this is something that I've already shown you yesterday, where some of my work has been used in real life, especially in cars. I would then kind of want to show you a history of how things have been evolving. We would go from 2D to 3D, both for image and video. We would then talk about one of my works where we do 3D human pose using physics-based constraints. We then talk about parametric 3D shape models such as PCA, SMPL, and GHOOM. Then fitting these parametric models to images and video, estimating texture, material, loose clothing and interactions. And of course, Avinash here is a world expert who has been doing a lot of work on non-parametric models. So I'm not gonna touch up too much upon that, and you can always check with him on those things. So I mean, we already talked about this, right? So here we do again human pose estimation, and based on that, we realize a few use cases. Again, here we do human pose estimation where we localize all the joints in our body, including the head. And so you can realize use cases such as, automatic fitting of this to the head. So, I mean, why should you be listening to me? Why should we learn about human pose and shape? Well, it turns out it's a very important problem in computer vision. And if you can solve it well, you can do a lot of things with it. For example, you can do action recognition, with which you can then do security and intelligence. You can do clinical analysis of gait pathologies and then use it in medicine. For example, you can help patients suffering with Parkinson's. You can do human-computer interaction. So you can interact with devices which have a camera, like what you saw in the Mercedes car. You can do markerless motion capture. You can do gaming, VR and AR. And when you say VR, it includes the metaverse, right? So suppose we were to interact with each other in the metaverse, in VR. So then we would first need to reconstruct all of you and me in that virtual space. So to be able to do that, we need to understand the human body. Now, since let's kind of see how we arrived to where we are today. So the earliest, say, capture of human body and motion was by Murray in 1882. So he captured this sequence of images with which he wanted to understand the human body better. So this was back in 1882. And then there was this seminal work by Johansson. And what he said was the motion of the living body was represented by a few bright spots describing motions of main joints, 10 to 12 such elements in adequate motion combinations evoke a compelling impression of human walking, running, dancing, etc. And this etc. essentially kind of maybe pushed the field in a little bit of a wrong direction, because then we focused a lot on these dots, on these joints, so to speak. Right? So what are these joints? Well, given a 2D image, the task of 2D human pose estimation is to simply localize these 2D joints on the image. For example, where is the center of the eyes, where is the shoulder, elbow, wrist, left and right, right? Now, people have been doing this for a long time. This was one of the, this is still, I mean, people did this before, so many decades. People did it before Bregler et al. In 1998 as well. But this was one of, one of the papers where it started to work decently well. But it is a very hard problem. For example, even for a human, it is very hard to say with 100% confidence where his right knee joint is, right? Because, so why is it hard? It's hard because the human body is a high degree of freedom configuration model. For example, if you have 14 joints, you have 28 parameters, and you need to find correct values for all of them. Because it's such an articulated structure, it can lead to complex self-occlusions, like you saw in the previous image. Also, self-similarity of body parts. For example, the hand, this and this, the contours of both the hands would look exactly the same, but we need to distinguish between them, right? So this is right and this is left. Large variations due to body type, clothing, lighting, viewpoint, and ideally we want to estimate these without any specific priors, without knowing that okay, it's a frontal person, the pose of the person, maybe background and so on. So we want to solve it for the completely unconstrained case. And of course, training data is always limited, but we seem to have some issues here. Okay, sorry about that. So yeah, training data is limited, though we have large enough data sets, especially in 2D. Doing this, for example, in 3D, you can, we'll talk about that, but you can understand, like because there is manual annotation, because you have to annotate manually, training data is often limited. This issue. This is, you have one? You have. Yeah, can I? Yes. So. Projector issue. Yeah. Okay, I hope it works. All right, fingers crossed. So pre-deep learning, right? Pre-AlexNet, what happened? So pre-AlexNet, we were using handcrafted features. So we were using things like Hogg, histogram of gradients, or shape context, based on part detectors, followed by a higher level spatial model. And it encoded only the gradient information. It was ad hoc trained. And so I'm talking about my story at NYU. I was a postdoc. Jan LeCun, who won the Turing Award in 2019, was my next door office neighbor. And Chris Bregler had done a lot of human pose. And we thought, okay, because AlexNet is working, maybe we should try this on human pose. So we did that. We published a ICLR 2014 paper, one of the first for human pose, and we beat the CVPR paper. So this is ICLR work. And we beat the last CVPR, which was based on handcrafted descriptors, just by using a very, very simple neural network. And what is this neural network? Well, the input to this neural network is a patch, right? You see these patches, and just forget about the this branch and forget about the bigger square. So let's just focus on the blue ones. So you just give it a patch, and this guy here basically says, okay, what kind of a patch is it? Is it a background? Is it a shoulder, elbow, or wrist? Right? So the first one is high if it is shoulder, then the second one is high if it's a wrist, elbow, the third one is high if it's a wrist, the last one is high if it's a background. And I mean, it already started working very well. So what we did was we improved it. Here it was patch-wise, right? It was a sliding window model. But then we moved on to this one-shot model where you give this entire image as input, and out you get these heat maps, which are basically response maps corresponding to each joint. And we did this multi-resolution work because there is so there is low frequency information coming in from here. There's high frequency information coming in from here. We had to do some some engineering to get it to work with this multi-resolution in this one shot setting. And we were so we got a huge bump when we did this, and I'll show you the results. But yeah, this was this was the first work using deep learning where we regressed heat maps for human pose. So so heat maps using for human pose using deep learning, this was the first work ever. Yeah, so this was a simplification, and it still worked very well. And what we had here was also a very simple spatial model. What is this spatial model? Well, what we want to do is, here we want to detect the final location of the head joint, right? The point between the eyes. And what we want to do is, we want to use the information coming in from the shoulder. Let's say we get these 2 dots for the shoulders, and we get these 2 dots for the face. And we want to use the information in the shoulder to finally find the correct face joint. And how did we do that? Well, we learned a kernel. So this is kind of the belief that if the face is at if the shoulder is at the center, the face should be somewhere in this region, right? And then what we do, we simply convolve, we do a correlation of this response map. So forget about the image, but just the dots with this filter. This is a learned filter, by the way. And you get a message, or say the belief from the shoulder to the face, that if the shoulder is here, the face should be somewhere here. If the shoulder is here, the face should be somewhere here outside the image. So that goes out. So then you say, okay, this is the belief that that the shoulder is giving me, and this is my own belief. So you call it unary, and this is the shoulder to face message. And you then integrate both of them, and you get the final position of the face. All right. So this was one very a very simple spatial model. There was one big problem, that these filters were large, say 128 by 128, and doing convolution correlation with such filters was very time consuming. So we then, so we wanted FFT convolutions. They were not present at that time, so we coded our own. So that is how we were doing deep learning back in the day. I wrote, say, volumetric convolutions for Torch, normal convolutions for Theano, because we didn't have them, right? So yeah, I mean, it was a fun time to live in, but it was also easy to maybe make contributions at that time. And so yeah, if you want to represent it as energies, so this is the final, this is the final score of the phase, which is basically in the log space. It's just the addition of the unary distribution and this belief that is coming from the shoulder. And if you want to implement it as a neural network, you have to make sure that, because there is a log, because we are adding in the log domain, you have to make sure that this is positive. So we make sure that, we have a soft plus on the weights and the biases, and on the activations that are coming in are already positive because of the ReLU. And this is how you phrase it in the neural network. These are some qualitative results, not interesting. I'll show you better later. But what is interesting is these are results till 2013, right? So this is on the y-axis, you have the detection rate, and on the x-axis, you have the normalized distance error. Meaning, so this is for the wrist joint on the flick dataset. And what it means is, let's say this 10, right? So it means that with 10 pixels, you get about, so with less than equal to 10 pixel error, you get about 40% of the dataset right. Okay. So this was my ICLR work, which I was telling you about, the 2014 work, which already beat, this model in say 0 to 10, which is interesting. Like beyond 10, I think the error doesn't really make sense, and it's already too far. This was Google's work. So Google did the first one-shot kind of a deep learning approach, but this is our NIPS 2014 work, which then kind of beat all of them by a big margin. So we went from say around 40 to like 60 to about 85. And this is when these kind of methods became good enough to be really used in industry. And this is when companies like Mercedes came knocking to see, if we could use them in their products. So this was a beginning. This was the beginning of something very interesting for me in my life. This is similar results on another data set. So the dotted lines represent the elbow and the solid line represents the wrist. The blue is ours. This one is Google's, and so this is Leonid. So this is also my work, but pre-deep learning and so on. Now this was like what people were doing for say the 2D joint positions. But then there were also people looking at the 3D shape itself, and they were looking at it, in the 70s already. So there was this model by Nevatia and Binford in 73, and then again Mar et al. In 78. And here he had basically a cylindrical model. So he had a 3D model consisting of cylinders, and by changing the parameters of this model, he could represent different kinds of humans and also maybe human-like animals like apes, etc. Here he had a generalized cylinders, and he then tried to fit it to range data. But again, like I had no convolutions, he had no range scanners. So he had to kind of build a range scanner to fit his model to range data. So, I mean, it was kind of difficult to maybe do a PhD back in the 70s. Then this was David Hogg in 1983. This was one of the best works till date. And this was a model-based vision, a program to see a walking person by Hogg. And what he did was what people did in that time. He created edges, and then he fit his model that you see here on this edge image. And this was so good that maybe this kind of scared. So, and if you look at, his model, so this 3D model, which has been projected here, it is kind of all hand coded, right? So these are basically cylinders and cylinders. So there's a class person, and the person class has a torso, and the torso has a head. I mean, torso is connected to a head, the head is connected to the torso is also connected to the arm, and so on. So it was kind of all very hand coded. And this probably worked so well that it kind of scared everybody away, and they said, okay, maybe we cannot do better. So people did not do too much work for this 1 decade. And then came, this classic. So let's talk about this kinematic tree. So the classical generative approach. So what Mar et al. Did in 78. So what you do is you represent, say, your human body using these cylinders. And these cylinders are connected with these 3D joints. Yes. And this is called a kinematic chain. So I'll tell you what that is. So there is a rigid body transformation for the torso. So for this whole body, you have one rigid body transformation, meaning there is rotation and translation. So if there is a body like this, you can translate it and you can rotate it. right? Every other joint is then parameterized only by rotations. There may be multiple degrees of rotation, for example, the shoulder, which is a ball and socket joint, or elbow, which is a hinge joint. So there is only 1 degree of freedom here. And this is a kinematic chain, meaning everything happens in the coordinate space of the parent. So you start by going from the torso. So suppose you want to apply this transform, suppose you want to rotate, so this theta 2 1x for the elbow. If you want to apply this rotation, you'll have to start from the torso. So you take your hand here. So you first apply the transform for the shoulder, and then you apply the transform for the elbow, right? So this is how you represent till date a human body or a human skeleton. Now, if you have this kind of a model, you can then try to fit it to multiple images. For example, you may know, you can estimate the cameras, or if you have given cameras, you can project it back to images, get some evidence from the image. And if you fit it to multiple views, you can kind of see that you will get a good reconstruction of the 3D pose, right? Then there was some work by Gabriela et al. His PhD thesis was, I think, seminal in 1996 already. So here you see that there is this indoor space, and he had these humans made out of super quadrics. So you can already see that this kind of looks like a woman, this kind of looks like a man. The cylinder doesn't look like a man or a woman, right? But here it kind of does. And this was a fully differentiable framework for optimization. So it was pretty cool mathematically what he had developed, but it was still simple shapes, multiple camera, and special tight clothing. Then this was one of my postdoc advisors, Chris Bregler's seminal work, again in 1998. And this paper has more than 1,000 citations. It's called Tracking People with Twists and Exponential Maps. So twists and exponential maps are a great way of representing rotations. So you can represent rotations using, say, rotation matrices. You can do it using Euler representation, using axis angle representation, but exponential or quaternions, which I'll talk about later. But exponential maps have a lot of advantages in terms of compositing rotations. So this is the Muybridge man walking. And right, so, and by the way, this work later, he created a company out of it later. This got sold in 2015, and he won a SciTech award, which is the technical award, the technical Oscar award. It was used in movies like Pirates of the Caribbean to do motion tracking. So if you have a very accurate mesh, you can then track it in a single view using this kind of an approach. Now, this is some of my work from 2015, 2016, where we were doing a few cameras. So there were a few GoPro cameras. So here we have only 2 cameras, and we are doing 3D reconstruction using this. And here we're not doing too much. We're basically just localizing the 2D joints and kind of triangulating, right? But it kind of still seems to work decently well. Here is another sequence. And then in ECCV 2018, we presented this work where we learned human pose from structure and motion. And I want to show you this video a little bit. So here you see that we have this just one image as input, and we then reconstruct the skeleton of this person in 3D from only one image, right? So these are some examples, some results. And what is more interesting here is the temporal model that we had. So if you do a per frame reconstruction, you'll get some jitter, obviously. But when we apply our temporal model, we get a jitter-free and not smooth motion, because you can always remove jitter by, say, applying a blur, by applying a smoothing filter. But you also do not want to, make it smooth. So here you see that the motion is realistic and not very smooth. And what we did was something very simple. We simply had a fully connected network to learn this smoothing, right? So this is near marker mocap quality, and it was well received. And this, again, paper has more than 100 citations. My PhD student now who did this work is a postdoc at my alma mater, the Max Planck Institute in Informatics. And here is another result. So what did we do? Well, we had first a model which ran on single images. And when you give it one image as input, it gives you the 3D pose. I'll show you how we do that. And then you give your the next network multiple, so say a history of these n-1 past frames of of the video, and it gives you the current frame, so the temporary refined 3D pose at the current time step. And then we also have a skeleton fitting step, because these may not correspond to a consistent skeleton, meaning the distance between the joints may change. But when you have a consistent skeleton, your distance cannot change, right? Because all you can do is just rotations. What we did was we also used weak supervision, and I'll show you how we use this weak supervision in the next slide. But here I want to show you some details of the model. So the input to the model are images such as this one. So before we explain the model, let's try to also understand that when you want to do 3D human pose estimation, you can have some data sets, right? You can have data sets indoors where you know the ground truth 3D position. But how do you do it for images in the wild, or say images from the internet? How do you get ground truth 3D pose for such images, right? So you cannot actually, or you will have to have a human animator animate the joints to kind of give you ground truth, which is again very, very tedious. So what we did here was we input images such as this one into our network. The network is basically a stacked hourglass model. People who know about the hourglass model, it's essentially an encoder decoder, a unit kind of a model. And this gives us these heat maps, so to speak, right? So a heat map may look something like this one. So this is our heat map. And from these heat maps, we can estimate X and Y by simply doing an argmax over the heat map. We also have a depth regressor module. So this depth regressor, in addition to the X and Y, regresses the depth value for all joints, right? So you have number of heat maps equal to the number of joints, and for each heat map, for each joint, you also have a Z prediction, and this Z is a single number. It's just a regression. We train 2D and 3D data to train for X and Y. So the X and Y is fully supervised, right? You have ground truth joint positions, which is easy to annotate. You backpropagate from it, and you can easily learn these heat maps. We use 2D and 3D data to train for X and Y, and we use 3D data and weak supervision to train for Z. So for indoor scenes such as Human 3.6, like the indoor scenes that you saw previously, you have complete supervision for Z. But for images such as this one, for outdoor images, you do not have the ground truth for Z. So we asked this question, can we still do something? Can we still get some signal out of my current prediction? This thing will still predict something, right? We'll give it this, we can train for this, but we will have some output here because we had some images from this data set, the 3D human pose data set. So we will still have some outputs here. So we ask this question, can we maybe regularize these values that are coming out? Can we kind of make them, can we do something here? And what we came up with were two additional losses. So now we are in a setting where we have these outdoor images. We have ground truth X and Y, but we do not have ground truth Z. Okay. So what are we saying? But we will still get some prediction, right? During training time, if we have this, we'll get some prediction. And we are saying that the prediction should be such that you should not have illegal angles. What is an illegal angle? Well, we know that our elbow will not bend in the other direction normally, right? So how do we encode this as a loss? So we want to exploit the flexon constraints of, say, elbows and knees. And we say for the right arm, the prediction is legal if the dot product between this vector nRs and this vector VWE is greater than or equal to 0. What are these vectors? This vector nRs is basically the cross product of the vector between the two shoulders and the shoulder and the elbow. right? So this gives you the normal to this plane passing through your upper arm and the other shoulder. And you say that the dot product between this and this should be greater than 0, meaning between this and this vector connecting your elbow and the wrist. And to then compute a loss from that, we simply exponentiate the the negative of this dot product, right? So does this make sense? So all we are saying is we don't know the correct value for this, but can we still back propagate some signal? Can we still have some loss? And one such loss was this illegal angle loss, and this is how we coined that loss. Similarly, this is a simpler loss to understand. The symmetry loss, here all we say is that for symmetric body parts, we know that usually the, say, left upper arm and the right upper arm, the lengths should be same. So we say that for the non-torso bones, the difference between the bone lengths should be minimized, right? So the sum of the difference of bone lengths is also minimized. Yeah. No? Yeah, whatever you do, can you bend your arm in the other direction? Yeah. Possible. Yeah, correct. But we are eliminating, yeah. So it's pruning the search space so that you're at least eliminating the incorrect angles. So you're still getting some, this is why it's weak supervision, because you get a weak signal from here. Yeah, yeah, go on. There's no loss threshold. The dot product should be greater than 0. So when is the dot product of this and this vector greater than 0? Yeah. Anything else? No. For elbows and knees, you do something like this. Yeah. Like what? I mean, you can, but yeah, I mean, this was the, yeah. Sorry, say that again. Sure, but I mean, so it depends on the weight on this term also, and yeah, like it will kind of go towards smaller angles, but it will explicitly, so it's also exponentiated, right? So yeah, you're right, but it works because you do have some 3D supervision also. It turns out to work, and we could only think of this one. Yeah. Correct. No, so we are saying that, okay, for X and Y, you have a direct loss, right? Because you have direct ground truth, right? So there is no ambiguity there. But here we do not have ground truth. So can we still put some loss that we can back propagate here? And all these vectors are made up of X, Y, and Z, right? So this is where you can then back propagate this loss from here and here also. Yeah. Any other questions? All right. So I think this will help you understand. So this was also one of the first visualizations of this kind, where so here you have these three configurations, right? Here you have a pose with a illegal joint where the elbow is bent in the wrong direction. This is a pose with incorrect bone lengths. So you see that this bone length is maybe different from the other bone length, and this is actually a correct pose. And these graphs, here you have the X value of the elbow joint, you have the depth of the elbow joint, and the value of the loss. And the value, the lesser the loss, the better. So when you have only 2D supervision, when you have only the heat map loss, all these joints correspond to the same projection in 2D. And so all these joints, all these configurations have the same loss, right? Because there is no notion of Z. Because all these, I mean, the position of the elbow joint is same when you project it onto the image in all of these. It's only when you look at it in 3D that you see some difference. Here we enforce only the symmetry loss. And when we do that, we see that, like the correct one and the incorrect one, where the elbow is bent in the other direction, have the same loss. And this is the most interesting curve, where you have your illegal joint angle loss as well. And here you see that the third, which is the correct configuration, has the least loss as compared to the second and first configuration. And these are just not didactic figures, these are actually real curves, real values of loss that we obtain. And this may help you understand the situation better. So when it is fully supervised, when we have complete information about X, Y, and Z, then it is kind of a convex surface, right? Because then there is no issue there. Yeah. Yeah, for this loss function, yeah, it looks like the first configuration is worse than the second configuration. Correct. But the most interesting thing is the third one, not so much the first one. Any questions? No, this one is, sorry, third is, of course, no, third is not fully, this is just the correct pose, but this is a fully supervised setting where you have all the ground truths. Here you only have X and Y and the weak supervision loss from symmetry and illegal angle. Any other questions? Yeah, so that was very simple. What we did was so you have, say, these poses, and you concatenate, say, previous 20 poses, you put it into a fully connected, and you output one pose. Yeah, and this happens to be a very powerful, say, method to do temporal smoothing, which is, realistic. Any other questions? Yeah, we tried, because I think it was simple enough, and LSTMs did not work significantly better. We even tried temporal convolutional networks, 1D, 2D, everything, but MLPs were already doing the job. We did same number of parameters also in LSTM. I don't know the answer. I mean, I don't know why. I mean, it's difficult to actually understand this, right? I mean, we've been thinking about it, but I mean, one thing is we have a curve where you can see that there is, like when you have a MLP, every joint has the opportunity to interact with every other joint. Also, all temporal joints have the opportunity to interact with every other, but that's about it. So still doing 3D pose, we did this work in 2019 where it was a generative setting. We had a VAE, a CVAE, where we were generating multiple poses, and then we had this ordinal loss to choose between these multiple poses. So this was interesting, but this is maybe not real world use, so I will skip that a little bit. I'm more interested in the real world. This was our recent ICCV 2021 paper. There is no learning in this paper. All we do is I'll show you the video a little bit. I'll let the narrator do the narration, if you can hear, and then we'll talk about it.
We propose GraviCap, a new approach for joint markerless 3D human motion capture and estimation of free flight object trajectories from a single monocular RGB video. In contrast to existing monocular methods, we can recover focal length, object trajectories, as well as human bone lengths in meters, along with the ground plane's orientation, thanks to the awareness of gravity. The proposed formulation with human object interaction constraints ensure the geometric consistency of the 3D reconstructions and improved physical plausibility of human poses compared to the unconstrained case. PhysCap improves initial kinetic human poses with physics-based pose optimizer Yet it does not reach the accuracy of the proposed GraviCap in global position estimation. Our approach differs from these methods in that we assume scenes in which humans interact with objects and bring those to a free flight. During the free flight, the object's trajectory is parabolic in the 3D space and can be faithfully estimated relying on Newton's law of universal gravitation, assuming no other forces acting on the object, such as air resistance. Such motion is entirely described by the initial position, initial velocity, and the gravity vector, which our method estimates together with the human poses. Our scenes of interest abundantly occur in real life, for instance, while playing games or practicing sports.
Yeah, so I will, so basically what we did was we said that, okay, if we know the trajectory of, say, a ball, then we can constrain the joints of the body based on the trajectory, right? So that this was a very simple idea, and that's all there is. There is no learning. We simply do some optimization to improve upon the existing predictions. This is some real life work where we do squat counting. It's coming out as an app called Xammer, and this is based on just the joints. So the point here being that, and this is, by the way, 3D. We tried 2D, it doesn't work as well. And today, using 3D, say 3D human pose estimation or 3D joint human pose estimation is very straightforward. You can do it in MediaPipe, you can do it on your Android phones. It works in real time. So it's now very democratic and very accessible to everyone. We actually used MediaPipe's light model here. And like when he does it wrong, there's also the state of the back we calculate. We give them scores based on, if the back is bent, then it's not counted as a correct squat and so on. So by the way, we started with 2D because we're like, okay, maybe we can do squat counting in 2D. And then the algorithm, we added. So this is a rule-based algorithm to count the squats built upon the 3D joints. So in 2D, it fails because the camera angle is a big problem, right? I mean, then you need to know the pose of the person. So we had a calibration step where we asked the person to stand in a particular pose, but 3D just works beautifully. So the point that I'm trying to make here is that, this is already out there and it's ready to be used. Now, but there, with all this, the cylinder models or the joint model is that we don't look like this. And models don't then match data, because if you project this kind of a model onto data, which is, say, images, it doesn't match well. And systems using such models tend to be brittle. And we argue that we need a better model of human shape and motion. And so this is from Professor Black, Michael Black, who is one of the world leaders in human body shape and pose, specifically parametric models. So what he argues is that, joints are actually unobserved in normal settings, right? I mean, it'll be unfortunate if you actually see a joint, because joints are all inside the body. And contact is key. Joints don't touch the world, the skin does. And we want to model the surface of the body to reason about contact and expression. And our shape is also related to our health and how the world perceives us. So there is a need to go beyond joints and these cylinder models. And people have done a lot of things towards that end, all the way from, say, 73, where they invented a rain scanner and this cylinder model. And then there were, models in 96 and in 93 and so on. But they were still not like really realistic. And then this big breakthrough happened at, again, the Max Planck Institute, where Blanz and Fetter came up with this. So it didn't happen with bodies, but it happened with faces. So faces are actually easier objects to deal with, right? They have lesser degrees of freedom. They're usually, so these are all frontal faces. You have, you don't have clothing. You don't have a lot of the problems that you have with bodies. And so this is where the breakthrough happened. This was published in SIGGRAPH 1999, a morphable model for the synthesis of 3D faces. And here he could morph the shape and also the pose of the face, right? So he came up with this morphable 3D model of the face, where he could change the shape and pose of the 3D model. So the first face scanner looked something like this. And in 1989, the first 3D body scanner was kind of created. If you have, say, the 3D morphable model, they then did this inverse graphics, right? So you then try and fit your morphable model onto images and make the 3D model as similar as possible to the image, to the data. And based on this is my work from 2010, where we scan a bunch of people at the Max Planck Institute using this range scanner. You see that it takes a couple of seconds. This is my friend Andreas Bach. And this is then what the final point cloud looks like inside your point cloud visualization software. There are more than 150,000 points, 3D points in this scan. It just gets you the surface. It doesn't get still a lot of other details like texture, material, etc. So these are all the body scans that we created. And our intention was not to really create a morphable body model, but our intention was to actually change content based on this. So I'll show you some results of that. So this is our, shape. We call this the shape space. And later maybe I'll show you. And then we do some semantic mapping. So we can map these semantic attributes. So this is simply a Pca model. What you do is you scan a bunch of people. You then bring it to the same pose, maybe the A pose or the T pose. And then all these bodies have the same number of vertices. So you can then do simple Pca. But Pca may not vary, the attributes of interest to us. But then if you have measurements done or you measure it in 3D, you can then map those semantic attributes to those Pca coefficients. Right? Now, given a multi-view sequence such as this one, we could automatically fit this articulated body shape and pose model onto this human. So you see here that we fit this articulated body model onto the human. And once you have done that, since it's a clean screen background, you can replace it with a artificial background. Because we have a 3D model, you can also get details such as these shadows. You render these shadows, and then you can simply change the size of this person. So here we've reduced her height by 18 centimeters. And then this change is propagated throughout the video completely automatically. Similarly, we can also increase her height. So here we have increased her height 20 centimeters. And then the same change is then propagated throughout the video completely automatically. Right? So here we did this on a Baywatch sequence. So here we've rendered this person to look more muscular. And since we have a muscularity slider, you can render this person more or less muscular. And we all want it, right? So this should come out as a snap filter, I guess. But yeah, we have a patent on this. But there were issues in terms of licensing, IP owned by Max Planck and so on, because of which it did not become a real world product. You can do this manually, say using the liquify filter in Photoshop, but doing it manually is very tedious and time consuming. And then there is this other problem of making it consistent in time. Otherwise, it will look very jittery. So, right? Manually, it just doesn't work out. And how do we do it? Well, it's straightforward. The human body is parameterized by the pose. Pose is nothing but the skeleton. So pose essentially means the 6 degrees of freedom for the torso, and then 3 degrees of freedom for the shoulder, 1 degree of freedom for the elbow, and so on. So this is basically the pose parameters. And then we have the shape parameters, the Pca coefficients. And the measurements that we have are these segmented images. We call it silhouette images. So we measure the